everybody, it's Elisa. We are back and we're talking about the urinary system. This time we're going to start looking at urine formation. This is going to be like a multi-parter. So here's the first one. So for renal innervation, or the nerves to and fro the kidneys specifically, um, we're going to be looking at kind of, just so you know, like there's a parasympathetic division and a sympathetic division. And we know a little bit more about the sympathetic division, but like a lot less of the parasympathetic. So let's go ahead and get started. So the renal plexus is like, it's a complex of all the nerves and the ganglia that are wrapped around each one of the renal arteries. And so they are going to follow the renal artery into the kidney, and a lot of these nerve fibers are going to be picking up sensory information in terms of how the kidney is assessing maybe concentrations of salt, concentrations of oxygen, and all these other items that it's able to detect in the bloodstream. And so it's going to help give some important biofeedback to the rest of the body. Like if there's not enough oxygen, for example, key example, it might stimulate the production of erythropoietin so that we can get a little bit more red blood cells produced and circulating to hopefully increase the oxygen supply. So stuff like that. So anyway, the sympathetic innervation is coming from the abdominal aortic plexus. And so these are going to be stimulations that are going to reduce glomerular blood flow, meaning that we're going to kind of cessate urine production. We're going to hold back especially water primarily in the body. And so this is in response in some cases to falling blood pressure, because like the idea being if we can continue to keep a stable blood volume overall, then we can at least kind of get through whatever hopefully rough patch it is that is causing reduced blood pressure at that point. So this will stimulate the kidneys to secrete renin, which is an enzyme that activates hormonal mechanisms to restore the blood pressure, right? And so there's quite a bit of complexity in there, but we'll talk about renin a little bit later. So things we expect you to kind of learn in this chapter, or the takeaways are, we hope you can describe the process that the kidney is going to filter the blood plasma. We already started talking about that in terms of the glomerulus and filtering out or processing blood plasma into filtrate, and then either into urine or back into the bloodstream, actually. Also, we're hoping that you can explain the forces that promote and oppose filtration, and calculate to some degree the filtration pressure if given the magnitude of these forces. And we're also going to hopefully have you describe how the nervous system, the hormones, and the nephron itself can regulate filtration. So let's kind of go back to some of the basic stages. So we started looking at some of these parts of the nephron anatomy. So here's the glomerulus right up here, like a globe, right? So it's the globe. And inside we have afferent and then efferent blood flow coming out. So afferent's going in. And so inside, these teeny tiny little arterioles are going to kind of wrap around, and it's not shown here, the podocytes that are on top of them inside of the renal corpuscle. And so what'll happen is the blood plasma is going to kind of mainly be pushed down. The red blood cells and all that are going to be kept in. And the plasma is going to become the filtrate, right? So the filtrate is going to flow through a tubule system, right? Beginning at a proximal convoluted tubule system, and then it's going to go through the loop of Henle, or the nephron loop, and it's going to come out into the distal convoluted tubule system, and then out through the collection duct, right? Okay, and so that's kind of the basics right there. So some of the steps that'll happen, or that'll occur during this process, is number one, we're going to reabsorb the things that we want to keep, basically. The useful items are going to stay in, and we're going to return those back out to the blood from the filtrate. And this is going to happen a few times, just, kind of to clarify that. Also, we're going to have tubular secretion. So this is going to be, we're removing extra waste actually out from the blood. And so this is going to happen from the vasculature that's surrounding these tubules, right? So there's kind of this interplay where we're going to be sending things to these arteries, and then we're going to be taking additional items out of these arteries. And then finally, kind of on the last end, so after we've, taken out and put back all of the items that we wanted, we've sorted through all the electrolytes or the salts or even the hormones in the body, what we're going to do in the final step is we're going to balance out the water. And so that's like the last thing that's going to do. So it's going to either return out into the bloodstream, or, if there's excess, it will go out in the urine as we send it out to the collection duct. Okay. So glomerular filtration is going to be the first step. So again, that's in the glomerulus, right? The kidneys are going to convert blood plasma to urine in these 4 stages that we looked at. So we're going to filter first through the glomerulus. Then we're going to go through paroxysmal convoluted tubule, as well as like the nephron loop proper, and then distal convoluted tubule until we're finally coming out through the collection duct, right? So distal convoluted tubule, loop here, and then proximal convoluted tubule right in glomerulus here, right? So we'll take back the items that we want into the bloodstream. We're going to remove a few additional things that we might not have gotten out in the glomerulus, and then we're also going to balance out the water, right? Mostly it's going to be water is conserved back into the blood supply. So the glomerular filtrate is the fluid in the capsular space, right? So that is after we've secreted out of the afferent arterioles, it's going to be all of that blood plasma that kind of is left in that space and is going to get pushed into the proximal convoluted tubule. Okay. It's mostly blood plasma, but the proteins proper don't really come out. So those will primarily be staying in the arterioles. Tubular fluid is the fluid from the proximal convoluted tubule, right, the PCT, and all the way through the distal convoluted tubule, right? So that's the DCT. Oops, let me cross that out there. And so these are items that have been removed or added by the tubular cells just kind of along that entire process. Remember, we have like kind of a balancing effect. And then after water conservation is complete, what we have and then what we're putting into the duct is actually urine proper. And this is kind of Itski's for it. Like whatever we produce by now is what we're going to be excreting in the urine. Okay, so here's like the coolest picture. Like there's this one, which is great, but then there's this one, which I love. And so what you see here is a podocyte, like actually multiple podocytes, and they've been colorized. And here's the cell body right here, right? Here's like the nucleus. And it has these feet, right? So poda is kind of what they're talking about. And see how they have like these like long fingers. And so they interlace with other podocytes. And they make it so the filtrate will come right out through those little tiny gaps. And I just think that's like the coolest picture. Okay. Glomerular filtration membrane. So what this is this is going to be the intersection of where we have the actual capillaries that are fenestrated, and what that means is they have these giant kind of gaps, right? And so they're not super big. They're not like a sinus big, like you can't fit a red blood cell through, but you can definitely get some of that blood plasma in and out, right? So this is the endothelial cells of the glomerular capillary, right, as it's going in. The basement membrane is, of course, the attachment point as always. The filtration slit is going to be where that plasma is going to travel out into the glomerulus. The filtration pore is going to be the exit point, right? The little fenestrations of the capillary. The foot process of the podocyte, we saw those like little interlacing kind of long fingers at the bottom of these like feet that these cool podocyte cells have. Things that can go through this type of filter, because this is like right here, this is what we're talking about. This is a filter. This is it. Water fits through, small electrolytes, a little bit of sugar, amino acids, not proteins, but amino acids, fatty acids, vitamins, urea, uric acid, and creatinine. And so they are going to flow all out into this capsular space, right? And then we're going to head over to the PCT eventually from here. Glomerular filtration. It's really interesting. So it's a special case of capillary fluid exchange in which water and some very small solutes from the blood plasma pass from the capillaries through the fenestrations into the glomerulus of the capsular space of the nephron. So the filtration membrane, as we looked at, we have like these three barriers that the fluid has to pass through. Like number one, it's got to go through its own arterial, fenestration, and we're moving through the space in the basement membrane, and then we eventually are moving through the podocytes and into the capsular space. Okay, so fenestrated at endothelium of the glomerular capillaries, remember, so like a regular continuous capillary looks like this, right? So there's no holes or anything. And so then no, you have a fenestration, you have kind of just a little bit, it's like poking holes in a hose, right? And then, when you get into the bones, like particularly like the marrow spaces, you'll have like, a sinusoid capillary, which has got these huge holes, and that's for actually dropping in formed elements of blood. So those are kind of like three different ones. So fenestrated is like right here. Okay. So the basement membrane, so it's the thing that's tethering it all together. Proteoglycan gel. So like basically what it is like whenever you have a gel, for the most part, you have some water. And so along with that water, you have a lot of like either protein or like strands, carbohydrates, strands of proteins, and they kind of interlock and interlace a little bit, and so you get like kind of jelly feel to it. And that can also include things like electrolytes, which could change the charge. So the thing is to remember they're fenestrated capillaries, like they're not sinusoid. So it's not a lot of large particles, right? They're not a whole lot. Um, right. So a lot of the proteins, so remember there's amino acids and then there's like long folded proteins, right? Chains that have folded in on themselves and sometimes dimerized, right? And they're pretty darned big. And so not a lot of the protein really escapes out. Just teeny tiny single amino acids are going to go through those components or that part of the three barrier membrane. So the filtration slit is the final one. So that's where we have those podocyte cell fingers and their overlap. Right, and so they are going to wrap around, and what it is when the fingers of these podocytes are kind of interlacing, they form the next barrier, which means that they just have these teeny tiny little slits, right? And so that's like going to prevent like large items to come through that particular stage of the barrier. Also, it's a little bit negatively charged, which means that negatively charged anions, larger ones, are going to be repelled. So, mostly it's a size related issue and it's somewhat charge related issue. But as long as it's smaller than 3 nanometers, it pretty much passes right through this membrane. Which means that we have all of this like kind of like a grab bag of items that have drifted over now for filtration. So we have obviously water, little bits of charged particles, electrolytes, glucose sugars, some fatty acids, some amino acids, nitrogenous wastes, as well as some vitamins like excess vitamins and other things. So some of these substances are small enough or of low enough molecular weight, and they're just simply bound to the plasma proteins, and they just physically can't move through. For example, calcium, iron, thyroid hormone, not as easily, unless they are unbound. So those are kind of like pretty quick. So kidney infections, trauma, damage, especially to anything like the nervous supply, but mainly what we tend to look for are it's damage or trauma to the blood supply. Um, can damage the filtration membrane altogether. And when that happens, sometimes it can allow larger proteins, such as albumin, to start, or even blood cells to start entering the filtrate, right? And so that's going to start appearing in the urine. And so what we end up doing is we can measure that. Um, new issue by looking at things like if there's protein in the urine, or if there's blood in the urine as well. So a lot of times we have people who are endurance distance runners or swimmers, and so sometimes they can actually have strained their kidney so much during this type of exercise that there's higher perfusion of larger molecules or even red blood cells, and so that might be something we see there. And it's kind of dangerous to the glomerulus. So some of these pressure rates or hypoxic states where there's just not enough oxygen because of that endurance exercise, the glomerulus actually will start to deteriorate. So we don't want to have like too much of that hardcore workout, basically. All right. So that looks like it's it. I hope this was helpful, and I hope you all are out there having a great day. Okay, bye.